Hello all, thanks for joining us. My name is Jamie Johnston. I'm Head of Global Systems at Bryden Wood, and I'm also the Platform Design Lead for the Construction Innovation Hub. So I'm going to be talking about construction platforms and how we think they're going to drive a particular level of sustainability and reduce carbon across the built environment. So for those who haven't heard this term, which I suspect is quite a number of people, the best analogy I can think of is IKEA. So you probably know when you go to IKEA, it doesn't matter whether you're buying a bed or a chest of drawers or a wardrobe or a bookshelf. A lot of the components are identical regardless of what the furniture is, but also the process you use to make the thing is identical. The book always looks the same. It always has the same format. You only ever need an Allen key, maybe a screwdriver and a hammer. So there's a lot of commonality in terms of the components and the process, but it means that furniture can now be made by virtually anyone. The other things I think are quite interesting about IKEA is you don't go to IKEA and buy a wardrobe, but you buy a kit of parts because it's small, it's logistically compact. You can get, if you've got a big car, you can get an entire bedroom's worth of stuff in a single trip. And when you get it home, you don't make it in the driveway or in the garden. You take that kit of parts to where you're going to build the wardrobe and you make it there and then. So there's a whole lot of we think really interesting aspects of that if we could apply it to construction would have quite dramatic impact in terms of not just carbon but also cost and productivity, etc. So there's a sort of a number of threads of this or strands of this that have actually been fairly consistent for a number of years now. So government's been on this journey particularly to increase productivity, and you can see here some of the key documents. So the BIM strategy back in 2011, the autumn statement 2017, both of them were predicated on a value proposition. So it was cost, value, carbon performance. The autumn statement 2017, the exam question wasn't off-site. So I think people often latch onto that presumption in favour of off-site sentence. Actually, the exam question was cost effectiveness, productivity, timeliness, and you now add sustainability. And again, one of the key outputs from the hub is the value toolkit. So cost was never necessarily the thing, and off-site was never necessarily the thing. It's working out how to derive better value from our social infrastructure has always driven it. To do that, one of the key things, so hopefully everyone's seen the construction playbook that came out at the end of last year. One of the big shifts in thinking is no longer talking about projects or necessarily programs or necessarily even sectors. One of the key features of this is to stop focusing on the difference between sectors and start looking for commonality. So what are the IKEA components that we can use across multiple building types? So you'll see this language appearing now around shared requirements, standardized interoperable components, because that is how we're going to start to dramatically shift things. If we're going to use components at across programs, we'll use them at a scale which is how you suddenly get into kind of much more of a manufacturing mindset. So the first iteration of that harmonized, digitized, rationalized demand was the piece of work the Construction Innovation Hub did last year. So we looked at £50 billion worth of future pipeline, government pipeline over the next 5 years. And you can see some of the numbers that came out of it. So 70% of that could be done with one type of structural platform. So if we had something that did an 8-meter span, that works for classrooms, it works for inpatient wards, it works for apartment buildings. You suddenly start looking for these commonalities that have massive repeatability. So superstructure is certainly one of them. But you also see things like less than half of a school or a hospital is actually kind of sector-specific space. Most of those buildings are circulation and plant space and storage and maybe dining, those sorts of more generic supporting functions. So again, it starts to leave something interesting about how you could apply this at scale, that you could allow the departments, say, to focus on their very kind of sector-specific spaces, but you could take big chunks of that offline and start to do, a greater level of centralized design, much more common, repeatable designs. And again, that's how you start to get into the manufacturing space. So we've been working with government and private sector clients on this for a number of years now. We use these numbers 0 to 4 only as a sort of internal shorthand to describe the sorts of functions. But you can see here there's a range of these covering everything from sort of very low cost rapid housing all the way up to sort of, these big span spaces. Platform 2, which sits in the middle, is the one that has the £35 billion potential pipeline. I'm going to show you an example of Platform 3, which we're delivering on site at the moment, and some of the metrics that we get out of that project. Once you've done that sort of harmonise, rationalise piece, one of our driving principles is basically to work out how little material we need to make the building and how few times we can touch and handle that material. So as you know, buildings are mostly air and commodities. So concrete, steel and things are obviously prices changing at the moment, but relatively cheap. So one of our driving things was saying, if you could meet all of the technical and aesthetic and performance requirements of an asset, but use the least amount of material to do that, move that material the fewest number of times, have it handled by the least number of people, working as productive as possible, that must be quick and cheap. It's the kind of real manufacturing, how do I drive out everything that's non-value adding? One of the key things that's highlighted in bold there is this idea of not trying too hard to get things off-site, but actually just working out where activity should be best placed. And I'll show an example of that. But again, I think that's a mindset shift that lots of people currently think MMC means off-site. To us, it doesn't mean that at all. It just means what is the most effective cost and time and carbon effective way of delivering assets, and that's what's driving this. We're also finding that as we're developing things for one platform, we can instantly use them for the others. So we're learning things on the Landsec project, which is commercial office, which we can instantly deploy in healthcare or pharmaceuticals or education. So again, that kind of IKEA principle that once you've got a good idea, you can use it in multiple bits of furniture. Once we have a good idea, we can use it in multiple sectors. But again, it means that we're starting to accelerate the journey because we're no longer learning things centrally. There's a repository for that knowledge. It starts to go into a kind of place where it can be disseminated. And that's how, again, how we're going to start to really increase the speed of adoption and accelerate the innovation around this space. So I'm going to talk about a project we're doing for Landsec. It's called the Forge. It's just south of the Thames, near St Paul's. It's next to the Tate Modern. It's two 9-storey office buildings. It's about 140,000 square foot of office space. But you can see here, architecturally not constrained. So I know it's one of the things that people get concerned about is whether these kind of manufactured approaches are going to, dumb down the architecture in some way. That simply won't be the case. And nor is it in any other aspect of your lives. You expect manufactured things to be beautiful and high quality and perform well, and that's exactly the same thing we're going for here. So you can see the building is very site specific. The massing and the shape and the form is very responsive to its context and the surrounding buildings. So architecturally, it's very highly attuned to the site it's on. But we've turned that building into a suite of kits of parts, structural kits, facade kits, MEP, etc. So the vast majority of this building uses very, very highly standard components, with a few bits that we would say were sort of mass customized to take up, odd angles of the site. So again, we've been able to maximize kind of site utilization without relinquishing the kind of standardization of design, which is again a thing manufacturing does very well. Automotive now, cars tend to be quite highly customized, but using completely standard components and completely standard processes. So just cantering through these, there's a superstructure kit of parts. So we focus obsessively on the superstructure, not because it's the biggest bit of the cost plan by any means, but it's the bit that unlocks all of the other components. So you can already buy facades that are, manufactured millimeter perfect. A lot of the inefficiency comes from fixing the gaps between the kind of millimeter perfect thing and the plus or minus 50 mil piece of construction that sits behind it. So just in the way the car chassis is the thing that kind of sets out everything else, we use these kits to get very, very accurate superstructures to which we can then clip in all the other kits of parts. But it also unlocks productivity in the design phase. So once we've developed our kit of structural components, super optimized them to be as lean as possible, we can then turn that into a digital set of components, teach them the rules around themselves of what maximum spans and things they can do. And it means we can actually automate the creation of the models. So this is a video showing a workflow where We modelled the core of the building sort of manually, but the superstructure using the kit of parts was generated automatically. And it meant that every time there was a change in the building, we didn't try and change the model, we just generated a new one because it was quicker to do that. So you can see here we're getting enormous then speed in the design process, which means we can try more ideas, test more ideas, more simulation. And again, that's driving us to better designed, better optimized buildings using these kits of parts. And then this is how that translates into assembling the building on site. So again, a bit like the IKEA building in your wardrobe, rather than try and drive everything off-site, we're turning the building into a repeatable kit of parts that can be very easy assembled. So you'll notice on this, firstly, not many people are required to put the building up. We're using a little bit of automation. These things are called reach stackers. The test here, this was a prototype, was to see whether we could make the entire floor plate from the floor below. So we raise up the components, clip them into place, we pump the concrete, it's self-compacting, low carbon concrete, a little robot levels it, and then we strike the shuttering and take the kit apart and recycle it. So no one needs to work at height. It's very, very safe. It's incredibly quick. You can see we're measuring things in minutes, and it turns the whole building process. It effectively turns the building site into a factory for making superstructure. Next slide. So the in situ concrete thing is very, seems counterintuitive to someone who expects everything to be done off site. But you can see here, so on the very left hand side, that's a shot of the quality we're getting on site, and it's, you know, it's like precast quality. The little yellow tabs are the MEP fixings already cast in, so our MEP kit of parts simply clips into position then. But you can see here the steps that we go through. We place the shutters, pour concrete, strike the shutters, move them up. So we're getting, because all the components are laser cut, because they're millimeter perfect, we're able to get the same quality of finish without all those additional steps. So you can see on precast, you go through the same process, but then you move the precast to a laydown yard, you cure it, you lift it, you transport it, you lift it, you grout it. So all of those are additional steps that adds time and cost and carbon. And if you go back to that initial set of drivers, least amount of material, handle the fewest number of times, etc., what we're trying to do is work out, can I get factory-like productivity on site? Because I immediately get rid of the downtime of the factory and the running cost and the transport cost. And again, I get much, much closer to that raw material cost. So we're doing these things which seem on the face of it maybe slightly counterintuitive, but again, it always comes back to that kind of set of criteria. Can we take steps out? Can we remove handling? Can we, you know, touch the material fewer times? The result of all of that, of course, in the superstructure is we get leaner components because we can spend more time optimizing them. We get less wastage, fewer vehicle movements. So all of that is contributing to an overall lower carbon superstructure. This building has about 20% less embodied carbon in it, and it's Landsec's first net zero building. So you can see here we're getting very high quality performing assets for Landsec, but at a lower cost and with less carbon. We then have the facade, as I say, already comes as a kit of parts. What we have done is very highly rationalize that, again, to get a much better quality, repeatable set of components that can be made much more accurately, clip into the superstructure and sort of very, very quickly clad the building. Again, because the digital, we could spend a lot of time simulating different U values, the glazing, different proportions of solid to glass. So again, we use that kind of speed and digital workflows to do more testing, to tune the U value to get a better energy balance. So this is all about working out, can we get more natural daylight, for instance, and therefore less artificial light? Can we get a better energy balance to reduce the need for heating and cooling in the building? So again, this is making better quality space, performing much better in terms of carbon. And then again, the MEP comes as a kit of parts. Because it's systemized, we could design variants of this. So we have one set of components which is a fan coiled, one which is chilled beam. So firstly, that means that Landsec can decide relatively late in the process how to service the building, which gives them more flexibility and gives better choice for potential tenants, which is fantastic for Landsec. It also means that replacement and maintenance and things moving forward is much easier because it's designed to be moved around. So again, we're building in kind of long-term flexibility and performance whilst getting all the benefits of these components. This again was the prototype, but again, you can see they're using the same things, the reach stackers to lift these components in. So very, very high productivity on site. Again, again, because of the compression of that, because of the applying that manufacturing thinking, that's also contributing to lower carbon. And when you start to combine these things, what we've been able to do is get very good floor to ceiling heights for quite lean floor to floor heights, which means the building volume is working harder. It means the cooling loads are smaller, the air handling units are smaller, the running cost is smaller, and there's overall less carbon. So we talk about this kind of chain reaction of benefits coming from bringing all of these initiatives together. And then last slide from me, and you can see here the sorts of metrics we're getting. So we're still working through these at the moment, but broadly it's coming in at a lower capital cost. You can see here 20% less embodied carbon, which is a fantastic result. Quicker and fewer operatives. So again, we were doing that for productivity benefits, but you can imagine in a post-COVID world having fewer people on site working at a higher productivity and building things has got to be a kind of, you know, a benefit moving forward. So if you imagine taking these benefits and magnifying it by the scale of that 50 billion investment, you can start to see how you can get some very big benefits to clients and to broader society through adopting this method. And that's why we think it's a, you know, it's a key strand thinking moving forwards. So thanks very much for listening, and yeah, we'll take some questions now.
Well, as Jamie said at the end there, we are going to take questions from the audience. So please, if you have anything that you'd like to put to Jamie, do use the chat or the question function on Swapcard. We're very happy to get those questions, and we'll do our best to answer as many as we can. Jamie, fascinating presentation, and I think perhaps a reset in expectations for a lot of people. As you say, we've got to divide modern methods. What we think about modern methods is often wrapped up with offsite, and you're making the point that actually we need to think about things in a more sophisticated fashion. One of the things that struck me looking at that video is, I mean, we hear a lot of talk about designing for disassembly, designing for the future, making sure that we're not building something that can only be modified by knocking it down again. That must be presumably part of your thinking as well, a very, very important part, presumably.
Yeah, it's interesting. So firstly, the kit of partsness, if that's a phrase, the fact that it's easy to assemble the building obviously means that to some extent it's easy to disassemble it. The work that, say, the Construction Innovation Hub did, the Define the Need report, actually showed that one of the things that we're using to define the platforms, as I said, is the kind of the structural span and the floor-to-floor heights. Actually, those are really common, or to a large extent common, across lots of different building types. So I think we need a more maybe nuanced debate about what do we really mean about sort of disassembly. My guess would be, given that the spans and the floor-to-floor heights are quite common, you might build the superstructure for sort of 120 years or 200 years or something, and design the facade as a 30-40 year life cycle thing, because it's, in my head, it's easier to disassemble and recycle, say, the facade and the fit out, maybe the MEP, than it is the superstructure. But also, if you look at Victorian buildings, Victorians built these incredibly robust, massive brick edifices that have been multiple different functions over 200 years. We rarely knock down the superstructure. We just kind of fit it out and go, actually, I could make it into schools or open plan offices or loft apartments or something. So I think that's a more interesting debate we should be having about what do we really mean by disassembly. How much do we really expect people to disassemble things? And the phrase, I think it was coined in the 70s, sort of long life, loose fit, I think is a better description of what we should be thinking about. But we need to start answering some of these questions now, I think.
Yes, yeah. Well, as you say, I mean, different types of buildings with different floor-to-floor spans and things like that. If you're thinking about perhaps refit in the future, you may choose those to be higher than you otherwise would, because it gives you more possibilities in the future. That kind of thing, I guess, is a consideration.
Yeah, absolutely. Yeah, so one of the things that the hub found is that floor-to-floor heights actually are reasonably consistent because they're based around the size of people. Again, that thing of don't look for the specificity, look for commonality across sectors, and because people are a certain height, it means you can get natural daylight 8 meters into a building. That's why 8 meter spans are so prevalent in schools and apartments and things. There's quite a lot of technical overlap that means that you could repurpose some functions very, very easily without even having to sort of overspec them. But yeah, I think these are the sorts of, now we have this kind of data set through things like the hub, through some of these sort of platform initiatives, we can start to really leverage that and say, well, what do we really mean about these things, and how should we use them to develop better outcomes longer term?
The little video that you showed of the floor plates being constructed from below was mesmerizing, and really interesting point about sort of rehearsing these things behind the scenes as well. Has that enabled you to reduce the amount of concrete that you're using as well? I mean, that you're getting a very nice finish, you're getting a very predictable result. Presumably, you can optimize in some fashion.
Yeah. So one of the key things for us was. Basically, people tend to over-engineer superstructure because of the way the sector is set up, and because of the way fees work. For instance, it takes quite a lot of time and effort to super optimize a design. So people sort of design a 300 mil slab, say, does that work? Yeah, on to the next one. They don't go, could I get away with 260, 265, 268? Where's the kind of cutoff point? One of the things about reusing these components multiple times is you can put tons of effort into doing all that simulation that I talked about and sort of really starting to optimize them. But also, people like flat slab because it's easy for the following trades, because you've got a nice flat surface, you can blast your pipe work and your duct work and things. We have the downstand beams, which means we have much thinner slabs in between the downstands, which is one of the reasons we're getting that 20% reduction in embodied carbon. But also, we think of the MEP as part of the system. It's designed to clip in between the downstand beams. So one of the things that would normally be a sort of a nuisance, actually, we see as a benefit that it's part of the system. So again, you have to think of these things quite holistically. But if you start thinking of everything as a kind of kit of parts, that kind of drops out of it. But you imagine the underside of your car bonnet. Like, there's no space left. Everything is very, very compact. It's all very well integrated. That's how we should start thinking about the MEP systems, and we need to start integrating it much better with the superstructure to get down sort of overall building volumes, to get the heating and treating things down, to get the life cycle cost down. So all of this stuff is telling you, I think we need to get much more closely designed, much more integrated, and productize these things rather than think of them as hundreds of separate trades all with their own kind of zones in buildings.
Yeah, and as you say, it's easier to optimize when you're doing things where you're repeating the same design over and over. A question here from Bill Firth from European Metal Recycling. He's obviously interested in the metal recycling side of the process that you've described. He's asking, is that kit of parts used you described based on primary steels, or would your system allow for reusable steels?
It would allow for. I mean, it would allow for any of it. There is, I mean, there's loads of stuff. I'm sure there's lots of interesting stuff happening in this space at the moment. Certainly, there's. We're limited on how much recycled content we can use in the primary steel. So I think that's a debate that needs to be had longer term. There's also, I think, all the big steel manufacturers are looking at only making steel from electric arc furnaces that are powered by hydrogen fuel cells. So again, all of these sort of materials conversations are in flux at the moment, but I think there's one strand which is looking at how do we use more recycled content, how do we get the testing and validation for that. One is how do we make the primary materials using less carbon and using the decarbonisation of the grid and things. So again, none of these are things we've got answers to. We're hoping maybe this sort of platforms approach creates a more sensible arena to be having some of those conversations, because when you're sort of boiling it down to kits of parts, there's a smaller search area to talk about, and you can maybe have a more detailed conversation. It starts to sort of ground some of these things and gives you a real place where you could land some of this material science and really understand the implications, rather than sort of sending it into the wild where every building's bespoke. It's very, very hard to keep control of it in quite the same way.
And just very quickly, we've got about a minute to go. A question about how do you persuade clients to adopt this approach, or are they hungry for it once you describe the benefits?
It's cheaper, it's quicker, it's lower carbon, it's higher productivity, it's more accurate, it saves you time, it offers you a better quality product. So the MEP allows Landsec to sort of make choices quite late, which gives them more flexibility for their clients. You can see more net lettable area. So all of our sort of big clients, GlaxoSmithKline, have been living in this space for a while. Circle Health, we've been delivering projects at significantly lower cost for healthcare than the normal healthcare rate. So clients are coming for the kind of speed and low cost, and they're staying for the sustainability and quality and sort of choice benefits. But it's why it's why government is backing this. It's why government's sort of talked a lot about this in the playbook. For instance, it's saying if you can take the the benefits we're getting for clients like Landsec, multiply it by the scale of the public sector, then that's how we're going to start to make some massive inroads into in sustainability and a load of other topics around construction.
Well, it was a fascinating presentation, Jamie, and a fascinating video to watch as well. As I said, seeing the concrete poured from underneath, you wouldn't imagine that that would work and produce such a beautiful result. But there we are. We've got the video evidence there. Thanks again, Jamie.
Thanks ever so much, Sean. Thanks.
Thank you.